you're welcome from a short break. Until now, we have tried to see what we can use to obtain the adiabatic work, and of course we've arrived because we have established a relationship that pressure times volume raised to the power K is equal to constant, where K is heat capacity at constant pressure Cp divided by heat capacity at constant volume Cv. So how do we get the adiabatic work? Now let us go. Generally, our work for a working fluid is equal to pressure times the V. And so we already established that pressure times V raised to the power K is equal to a constant, let's say C. And if I make P subject to the formula here, it's going to be constant divided by what? V raised to the power K. So what do? We'll go to this work formula and then substitute for this adiabatic work. If we substitute, in place of P, we put C over V raised to the power K, everything times dV. We shall now integrate from initial to final volume. To do the integration, we have that W is equal to C will come out, so have integral V1 to V2, 1 all over V raised to the power K dV. How do we now integrate 1 over V raised to the power K? This is not 1 over V. If it is 1 over V without any other power, let's say it's just power 1, then the result will be ln of the denominator. Here, this is K. We don't know the value of K. Is that okay? It's just like someone giving you integral 1 over x squared. This is not ln x, because if you differentiate the denominator, you can't get the numerator, not anything close to the numerator even. So in this case, what you do is to rewrite it as x raised to the minus 1 using our reciprocal law of indices, negative index law. Then you can now integrate using power rule. Add 1 to the power and divide by the power. And that's what we're going to do here. So that will be C integral V1 to V2 V raised to the power minus K dV. So are we now set for the integration? We shall add 1 to the power and divide by the new power that will result. So this is C. We open up brackets. If you add 1 to this power by integrating, it to be V raised to the power minus K plus 1 divided by that new power minus K plus 1. And then our limit of integration, V1 to what? V2. What do we do with the limits of integration? We substitute for what we obtained in the integration. So upper limit there minus lower limit. So that gives us the adiabatic work to be C, open bracket. In place of this V, I'll put upper limit, V2. Alright, raised to the power minus K plus 1 all over minus K plus 1. Then minus, in place of this V again, you substitute your lower limit, that is V1 raised to the power minus K plus 1 all over minus K plus 1. Alright, so this is the term that we have obtained. Now, if we open up the brackets with our C, what are we going to get? W will now be equal to, now, you watch this. If this constant is multiplying this V2 is final volume. It means that the constant will be operating at the final state of the system. So we'll call the constant C2. Alright? So I'll put C2 V2 raised to the power minus K plus 1. And that will be minus C1 V1 raised to the power minus K plus 1. Take note that the denominators are the same. So just like LCM, you can pick one of the denominators. So you have minus K plus 1 there. And so what do we now obtain? This constant C2 is equal to pressure times volume raised to power K, where the P there is P2, V there is V2. Then when you come over here, C1 will be P1, V1 raised to power K. Look at it here. Take note that P is equal to C over Vk. And from here, we notice that the constant is pressure times volume to power what? K. So at this point, we are operating at the final state of the system. That C2 will become P2 V2 raised to power K. Let's substitute that and see what we'll get. Our W will now give us, for this C2, I'll substitute P2 times V2 raised to power K. Take note that it is multiplied by V2 raised to minus K plus 1. So I'll now say times V2 raised to power minus K plus 1. Then I'll subtract C1, which will now go as P1 V1 raised to power K, or multiply by V1 raised to power minus K plus 1, all over the denominator, which is minus K plus 1. Take note, minus K plus 1 is the same as 1 minus K, because I'm going to rearrange it in the next step. And so this will be W equal to, did you notice this is V2, this is V2, you are multiplying it. Indices, another product rule of indices or multiplication law of indices, says that if you multiply the same bases, pick one of the bases and what? Add the powers. So we're going to have P2 times, I'll pick one of the volumes, then let us add K to minus K plus 1. If you add K to minus K plus 1, it will be K minus K, which is going to give us 0, then plus 1, which will give us 1. So this is P2 V2 raised to power 1. No need of putting the power 1 there. Then minus the same thing here, you have P1 V1. The KK's will go off if you're adding the powers. Divided by the denominator, let me just write it as 1 minus K. And this is the adiabatic work. Equation 4 star. Please memorize it, very important. This is what we've really been looking for. Now, if I choose to multiply the numerator and denominator by minus 1, what would this equation look like? Let's do that and see. So I'll say or. If you multiply the numerator and denominator by minus 1, multiply the top here by minus 1. This final state will become minus. This initial state will change to what? Plus. Because negative sign changes sign, you know that, right? If you use it to multiply. So this becomes P1 V1 minus P2 V2 all over. The denominator, you have to multiply also by negative, so that you'll be mathematically consistent. And that will give us K minus 1. These two equations are the same place, don't get it confused. Did you take note, when the numerator is final state minus initial state, the denominator was 1 minus K. And when the numerator is initial state minus final state, the denominator became what? K minus 1. Alright, now we have obtained the first-hand adiabatic work formula, good, in terms of pressure and what? Volume. In the next video, we're going to see how we can obtain this equation in terms of temperature. Why? Look at the numerator. Did you take note that it's simply changed in PV? That numerator is simply changing what? PV. And we know that PV is equal to what? nRT. Which means we can also write the numerator as what? Change in RT, where N is 1 mole per se. So, in the next video, we're going to see that, how we'll get the equation in terms of temperature. Alright, still on the adiabatic work formula, we've obtained the adiabatic work formula to be W equal to change in PV, which is P2 V2 minus P1 V1 all over 1 minus K. Or we can write it in terms of P1 V1 minus P2 V2 all over K minus 1. Like it was stated earlier before the break, the numerator is actually changing PV. Alright? And for 1 mole of the working fluid, PV will be equal to RT, because N there is 1 mole. So instead of nRT, it will simply be RT, because N is equal to 1 mole. Which means that the work can be written in terms of temperature as these. Okay, W equal to change RT, where this change RT represents change PV in the order P2 V2 minus P1 V1, which means that the change in temperature here will be T2 minus T1, because the denominator is what? 1 minus K. Alright, now we notice that R is a constant, universal gas constant, it doesn't change. Therefore, the change in the numerator will actually be affecting the temperature. Good, we can write the equation in this form, which will now give us work to be equal to universal gas constant times change in temperature T2 minus T1. Remember this order because the denominator is 1 minus what? K. Now, if we want to rewrite it as K minus 1, it means we have to multiply the numerator and denominator by minus 1. We did something like that earlier on this formula previously before we went for break. Okay, having said that, multiplying the numerator and denominator by negative 1 will reverse the order of this temperature change to T1 minus T2. While the denominator will be K1, will be K minus 1. Look at it in this order. So this equation 5 star is also another formula for adiabatic work in terms of what? Temperature. This equation and this equation are the same thing. Is that okay? It's just the change that was introduced as a result of multiplying numerator and denominator by minus 1. Okay, I prefer using this, the T1 minus T2 format, because this K, I don't know the value, it may be greater than 1. Take note that K is not expected to be 1, because if it is 1, then it means that the work will become what? Infinite work. Okay, now let's move on and see if there is another format we can get this equation. Okay, very interesting. You recall that our K is equal to Cp over Cv, is that not so? So we can write this equation as RT1 minus T2 all over. In place of this K, I will fix in Cp over what? Cv minus 1. Which of course, if I work out the denominator LCM, is going to be RT1 minus T2 all over. Okay, you are subtracting a whole number from a fraction. The easiest way to go is this numerator Cp minus the denominator times the whole number, which is Cv, everything divided by Cv. Mathematically, this denominator Cv will go upward. Is that okay? To multiply the numerator. And if it goes, we're going to have R times Cv, open bracket T1 minus what? T2. Everything divided by Cp minus Cv. And do you remember? We stated earlier that the relationship between R, Cp, and Cv is giving us R equal to Cp minus what? Cv. Which of course tells us that Cp is greater than what? Cv. Okay? We are going to state the reason for that. Just remember where we encountered Cp, isobaric process, and then Cv, isochoric process. We're going to state why Cp is usually greater than Cv. So that being the case, it means that this denominator as a whole you are seeing here is actually equal to what? R. And if that is the case, then the R term can cancel. And once they cancel out, that is this term here can cancel. So let me cross it. We are going to be left with work to be equal to Cv T1 minus what? T2. This is equation 6 star, still used to calculate adiabatic what? Work. All in all now, we are done with obtaining our adiabatic work. Remember that the adiabatic work is equal to minus change in what? U. You can see this very clearly. This Cv open bracket T1 minus T2, we encountered it, very similar to this in isochoric process. The only difference is just the order of arrangement of the temperature. Okay, which we can actually work on if we know that W is equal to Cv T1 minus T2. If I make change in U subject to the formula here, just like we saw from the base formula under adiabatic process, it's going to be minus W, is that so? Which will give us change in U to be equal to minus Cv open bracket T1 minus T2. Because T1 minus T2 is the order of arrangement here, which again bounces back to, if this negative affects this term inside, we're going to get Cv open bracket T2 minus what? T1. Okay? As what we obtain under isochoric process. So that's just that. Once you get your W, your work, to get your internal energy for adiabatic process, simply multiply the work value by what? Negative. And so if you're solving work for adiabatic process and you know the temperature and heat capacity at constant volume is given to you, you can simply use change in internal energy formula under isochoric process, that is isometric process, where change in U is equal to NCV T2 minus what? T1. Then to get your work, multiply your result by -1, you get your work for the adiabatic process. In the next video, we're going to treat the polytropic process. How we treat polytropic process, you should know that it's similar in terms of the work with adiabatic. The only difference is this constant K. Over there, we use N, alright, which is just an index constant.